That's not going to be the issues. All right. So if we look from right here, I only want to talk about the 0th order rate law. I don't want to talk about the 1st order rate law, just the 0th order. Okay. So what we're going to do is as follows. Let's just look at Margot's graph, and we're just going to talk through the points from right there. So let me go back and find Margot's. Go to 1. Wrong chapter. Don't need some from Land's End. Haven't gotten Margot's yet. Still haven't gotten Margot's yet. Oh, there it is. Okay. And Jen votes for Tuesday on her test. Okay. Thanks for sending that. All right. So here's what Margot got. Okay. This is just by looking at the data. Okay. And everyone should have gotten this. So this is the data for Matt's gas tank. What we see, here's the volume of the gas tank as a function of time, and here's the rate of gas loss as a function of time. Is everyone happy with that?
Yeah.
Okay. No questions about it. You're just graphing and going on top of that. So let's run through the questions. Okay. The questions asked, if I go back and play through, and I'm just going to read them all. Plot the rate of gas loss as a function of volume left in the tank. Why do I care about making that graph? Why am I so stressed out about plotting the rate of gas lost as a function of the volume? And this is where people mess up. It's right here. Okay? The problem is, what did we say is the form of any rate law? Rate is proportional to what for any process? It's proportional effectively to the amount of stuff. Now, when we're in the lab, that amount of stuff has units of what?
Moles.
No.
Per liter.
Concentration. That amount, but would everyone agree that concentration really is measuring amount of stuff? Okay? We don't measure it with respect to moles. We measure it to moles in a particular container because everyone's running around the same container. But here in this case, Matt didn't do it that way. You didn't worry about moles per liter. You just worried about amount of stuff. Okay, that's what I did. So therefore, not just amount of stuff raised to a power. What we argued from the beginning is this was a general mathematical statement that allowed me to relate the rate to how much stuff I had. Why do I want an exponent up there? Why not just leave the exponent as 1?
Because you don't know if it's 1.
You don't know if it's 1 or not. You limit yourself too much. You let the math determine what the exponent is, what the order is. So therefore, how did we turn that into an equation? Rate is equal to K times amount of stuff raised to the A. And we call that K the rate constant, which in chemistry depends on temperature. But we're not worrying about changing temperature right now, so it's not a big deal. So therefore, why did I ask you to graph this? What is this graph?
The rate.
Isn't it rate? No. What is this graph?
Rate versus volume.
Isn't it rate versus stuff?
Yeah.
If we think the rate law has this form, what do we need to graph in order to figure out what the exponent is? Rate versus stuff.
Yeah.
And when we graph rate versus stuff, we got a horizontal line. We got it. I mean, there's no deducing here. We graphed it. It was a horizontal line. What does that imply about the value of A?
0.
It's 0. The value of A must be 0 because rate versus stuff's a horizontal line. Done. Why is it a horizontal line? I don't know. I graphed it. It's horizontal. That depends upon the geometry and what's going on in Matt's gas tank. But all I did here was graph rate versus stuff and got a horizontal line, which must mean that A must be 0. Yes?
What if you had two different, like, in a chemical reaction, what if you had, like, A and B?
Well, then what we'd have to do is we'd have to set it so that one of the things didn't change much during a reaction. That's a very good question, all right? For right now, when we're looking at these graphs right this second, the graphical method, we're going to assume we only have one reactant, okay? When we have multiple reactants, we have to do a little bit of massaging, which we will talk about. What you have to do is you have to effectively remove one of the reactants from the problem, okay? And the way you do that, it goes back to the bleach problem that started this whole thing. We make sure the concentration on the reactants is so big that it effectively doesn't change over the chemical reaction. Okay? But here, we're only worried about one thing right now, okay? It's the volume. Now, note, graphing rate versus time may be nice, but is not useful. Because the rate law says the independent variable is not time, the independent variable is stuff. Okay? It's stuff. So therefore, what's the rate law for this process? The rate law then, for this process, according to the data, is rate equals K. Because I don't need to write stuff to the zero. I can write stuff to the 0 power, but it does me no good. So rate equals K. For $64,000 in the new car, what's the value of K?
0.7.
It's 0.7. Why?
Or negatives instead.
No, it is not negative 0.7.
Because rate can't
Because rate is always positive.
Okay.
So right now, I understand that where the negative could be coming from if you look faster to the graph, but we always define rate as positive. Okay? So what's the value of K? It's 0.7. How do I know it's 0.7?
Because I've looked the line.
Why?
What's the value of the horizontal aspect of the line? It's 0.7. How do I know? I looked at the line and it said, hey, I'm 0.7. Okay? So therefore, for this equation, rate is 0.7. Now, that's got to have some units. What are the units of the 0.7? Not moles over liters. It's liters per hour. Why? What are the units of the rate? Liters per hour in this problem. Therefore, what must be the units of K? Liters per hour, because rate equals K. Okay. Now, here comes the kicker, the most important thing ever. I can't stress how important this is. This is the light bulb moment. Okay? We want to see the light bulb start to go from this to at least that for a second. Okay? Do it again. Okay? What we really want is this. Okay, that's what we want by our test. Okay? For right now, I'd settle for this. Okay? And maybe even that. All right? Here's the light bulb moment. Is there any relationship at all between the two graphs?
Yes.
Yeah.
Yes.
Yes.
The bottom graph will always give me the rate law, because by definition, what have I graphed? The rate law. But can I get that information on the bottom graph just by looking at the top graph?
Yeah.
In fact, what is the mathematical equation for the top graph?
Light.
It is volume equals what? Negative 0.7 t plus 10. It is volume equals negative 0.7 t plus 10.
So if you're graphing volume as a function of time, the K will always.
Y plus 10.
Because the initial value is 10.
Oh.
The
Okay?
K
I mean,
will
it's,
always,
I'm just pulling it right off of here. Okay?
or like the slope of it will always be the rate.
Do you see any correlation between these two?
Slope is equal to the.
Well, it's interesting that the slope just happens to be what? Which is what?
Okay.
The rate constant. Because the rate constant is the rate. And what does slope measure?
The rate.
Rate. And not only that, what's true about this process? What's true about the rate?
It's equal to the constant.
It's always the same.
So what if it's squared? How
Huh?
would you
I don't know. I haven't gotten there yet.
That's the
So there you have it.
You're blowing my mind there. Let's start with 0. Okay? So notice something. The reason why this graph is constant, excuse me, rephrase that. The reason why this graph is horizontal, pull the wrong, sorry. Okay. The reason why this graph is horizontal is because what's happening to the amount of liquid in Matt's tank at any time?
It's always the same.
It's always the same. In fact, if I graph the rate versus anything, the rate versus my amount of hair, the rate versus Ruth's understanding, the rate versus the number of goals Margot will score in the next 24 months, if I graph rate versus anything for this plot, what am I always going to get?
Yeah, horizontal.
I'm always going to get a horizontal line around 0.7. Because what's true about the rate?
It's constant.
It's constant. So therefore, if I plot volume versus time and get a straight line, what does straight line say about rate?
It's constant.
It's constant. So if I graph amount of reactant versus time and get a straight line, it's got to be negative slope because reactant's got to go away. What does that tell you right away that rate versus anything will be?
Constant.
Not just constant, it'll be horizontal, okay? So therefore, since it's horizontal, what does that say the rate law has to be?
A constant.
Not only that, it's got to be linear. So what does that mean? What that says is that says, I gotta find it on mine. Let's go here.
What's the difference between
This
the
makes
rate
more
and
sense.
The rate is how fast something goes away, right? The rate constant is just the proportionality constant between rate and stuff. That's all it is. Okay? That's the sort of question that we want to address today. That means you've been sitting on the periphery and never really thinking about it deeply to that point in time. The rate is how fast the material goes away, right? What's the rate constant? No, Margaret's going, I'm utterly confused and I'll never get this. I see it in your eyes. Okay? Am I right?
Yeah.
Okay, good. So, no, I can see it. The rate is how fast the material goes away. The rate constant is just what? It's the proportionality between rate and stuff. For zeroth order, rate and rate constant are the same thing. From what we just did. All right, I want you to go back and watch that. We'll go back and watch it again. Okay, now, so notice something. You have two graphs. One graph is stuff versus time. The other graph is rate versus stuff. If this graph is horizontal, what does it mean this graph has to be? Not just linear,
Wait, why couldn't you be positive?
because the problem is it's reactant, it's got to go away. Okay? And what's the equation of any line? This would be stuff is equal to mt plus b. That's because it's a line. Where m is the what?
Slope.
And the b is the y-intercept. And the y-intercept represents what? It represents the initial amount. So in chemistry, that would be mt plus what we usually call stuff zero.
Yeah.
And stuff zero is the concentration of the amount at time t equals 0. That could vary. Matt could have started with 20 liters as opposed to 10. Whoop-de-doo. Okay. Well, if Matt had started at 20 liters as opposed to 10, how would the graph have changed?
It just would have.
They just would have moved.
Or if he started at 5 liters as opposed to 10, wouldn't it have just done this?
Yeah.
And at 20 liters, it just would have done that, right?
It would have just been parallel.
They would have all been
And
parallel.
the rate would be the same.
The rate would be the same. Because the rate doesn't depend on how much stuff Matt has, it depends on the whole. Okay? All those processes, regardless of how much Matt starts with, they're all zeroth order. They all don't, let me say it again, they don't depend on how much liquid Matt has on the tank. That's what zeroth order means. It's constant. Okay? There's a very big important process in the history of college students. Alcohol loss in the body is zeroth order. That's why if you go look at graphs on that, and I'll show you some tomorrow, that if you look at the amount of alcohol loss as a function of beers you consume, they will tell you you can consume like 1 beer an hour and still be under the legal limit. And the reason for that is that your liver processes alcohol at a constant rate. So if you drink 2 beers, it's going to take you twice as long for your body to process out that alcohol because the rate of losing it's constant. And if the amount of alcohol per beer is the same in every beer, it's that way. There are many processes that are zeroth order. Zeroth order is always born. Okay. Margaret and then Margot.
You have to have the first graph with the second.
Nope. You've done a lab, we didn't have to have the first graph. Someone could just give you rate versus stuff.
Well, yeah, but you have to know the rate.
Yeah, you have to know the rate, yeah.
So you
But if I
have-
know the first graph, I can get the second graph, right?
Yeah.
But what's interesting is if I know the second graph, it implies what the first graph looks like. The important thing here is these graphs do what to each other? They talk.
Yeah.
Because how fast the stuff goes away depends on the amount of stuff you have depends on how fast the stuff goes away. They talk. Now, those of us who are in calculus, that talk is the derivative in the integral. Okay? Now, if you're not in calculus like me, I have no idea what these things are. But what you're looking at right there is the fundamental theorem of calculus. Beep, 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 beep. Okay? And in fact, for those of us in calculus, this is why it's called the integrated rate law. It's integrated using an integral. It's unfortunate that we use that terminology in chemistry, because if you're not used to calculus, it just seems like that word means nothing. Okay? People who are in the middle of calculus or have had calculus see this stuff like this. Okay? To a person who's experienced in calculus, everything we spent the past 3 days on, they will understand in 5 minutes. If you haven't had calculus, it gets really hard. Okay? That's why we're doing it another way. But for those of you in calculus, we'll still see if it makes, works for
So
us.
integrated rate law, like, that means the two.
So what I say is the integrated rate law is the graph of stuff versus time. Okay?
Graph of stuff.
Stuff versus time.
Okay, and then changing that to rate.
Right, rate versus stuff gives you the rate law. Devesh, Sam, then we'll go back to Margaret. Quickly.
Why would the derivative of stuff versus time be stuff for stuff to rate?
The
to stuff?
independent variables are different. You are absolutely correct. It's not a simple one-to-one conversion.
Okay.
However, if I know one, I can get the other one for free.
Okay.
Because all I need to do to get the real rate law is I first have to take the derivative, but then I do have to graph with respect to something else. You're
Oh, wait.
absolutely correct. One is not simply that you can't just take the derivative of one and get the other.
Okay.
But through the derivative, I can obtain one graph from the other.
Okay.
That makes sense. Okay.
And then to find the rate versus stuff, you need to know the instantaneous.
Yeah. And that's why the average rate here won't help you at all.
Okay.
Now here it will, because
So
it
this
turns
is
out
why
that-
you need log or
Right. Now here it turns out since the rate's constant, but as we'll see in a second, that'll change. Sam,
Will you expect like first and second rate law on the quiz?
first and second order rate law? Yeah, they might say, well, if we say the order, what they're saying is what's the exponent? Huh?
I use that.
Because this won't be on your quiz.
Oh.
Your quiz is just what we talked about on Tuesday. None of this would be on your quiz.
Oh, like where you divide it?
Yeah.
I like that.
Manish.
So for
And I'll go back to Margaret.
So for the part with where the half-life would change, it would just be half-life. It would take longer for.
All right, so let's answer that question. The last question dealt with the half-life. Well, by definition, if the graph, going back to Matt's data, if the graph is this, going back to Matt's data, let me pull it up here. Where we go? Here we go. Going back to Matt's data from right here, notice something, okay? Okay, interesting. If Matt started at 10 liters, the half-life would be the time it takes for it to get to 5 liters. And in fact, I can just read that right off the graph. I mean, I can also prove it, because the issue becomes 5 liters is going to be roughly 7.13 hours. Okay? Now, I can also do that algebraically, because if the equation is volume is equal to, what was the slope here? Minus 0.7. Minus 0.7 t plus 10. How can I find the half-life? Plug a volume in of 5. And if you do that, you'll get a time of 5. You'll get a time of 7.13 hours. But here comes the question. Does the half-life change with the initial amount of gas? And the answer is yes. Because if you're always losing 0.7 liters per hour, and I start with 10 liters, it'll take me 7.13 hours to get to 5. But if I start at 20 liters, to get to half-life, I've got to get to 10. So therefore, it will take longer. If I have 5 liters, it'll take less time. Now, and I can go in and calculate what those would be, because the only thing I would be changing there is the initial amount. It would be minus 0.7 t plus 20, or negative minus 0.7 t plus 5. Okay? But the thing I want to bring home is, both of these graphs give me 2 different ways to get the same data. If I graph stuff versus time and get a straight line with negative slope, I know it's 0th order. Or if I graph rate versus stuff and get a horizontal line, I know it's 0th order. The issue is that in the lab, this data is much easier to get than this data. Rate data is a nightmare to generate in the lab. Because how do you get a piece of data that tells you how fast? That's hard. But here's what's even cooler. What if I graph something that's not the stuff, but it's proportional to the stuff?
It would still give you the same.
It will still give you the same information because once again, it doesn't, the details of the graph are nice, but what about the graph tells me it's zeroth order? Say it again.
Shape.
One more time.
Shape.
One more time with feeling.
The shape.
One more time with super feeling.
The shape.
It's the stupid shape. The shape tells me the information. And if I graph something proportional, what's going to happen to the shape? It will stay the same. Now, will the details in K and all that change? You bet. But will it still be a line?
Yes.
Yes. Okay.
Okay, then what's the difference between the top one and like a proportional or like a first?
This, if I'm fitting it, this obviously is not proportional data because by definition, proportional data must have a y-intercept of what? 0. This is not proportional data. Okay? It's not because it doesn't have y-intercept of 0. It's just linear.
What would x to the 1 look like?
X to the 1 would look like this.
It will be different.
Yeah, it'd be proportional. Which obviously this isn't. Okay. Jenny.
How would the rate of gas loss as a function of time, a function of volume, change if the first graph was a parabola?
That's a good question. Let's find out. Okay. So far, 0th order. This should help you with that last question on the website, which will be open again tonight. Okay. Manish.
Will we deal with graphs volume versus time where it's a 0th order, so it would be like an inverse function for the rate of gas versus volume? Like, will we deal with 0th order functions as the okay, yeah.
I have no idea what you just asked. That's okay. We deal with 0th order. When you say we just dealt with 0th order
Or
functions.
like, no, as
Oh, if the rate were 0th order?
not if the rate, if it was if the volume versus time was 0th order.
If the volume versus time was 0th order, that is going to be the most boring experiment of all time. Think about what you're saying. Let's watch the volume never change.
Yeah.
Okay? I'm going to tell you right now, there's no chemistry happening.
Yeah.
You see what I'm saying? All right. The volume versus time, it's not going to happen. I mean, yeah, we could go graph it. It will be 0th order with a K of 0. You know, we're not going to see that one, Manish. That would be a waste of our time. All right. Now, here comes the second graph. This is for Margot. Okay. And we're going to kill that because I don't know what Matt and Co. are doing there. But here's what you got for Margot's second graph. All right. And there is one piece of information. It looks like that Matt decided that the initial amount of money for Margot was $1,000. And Matt had some value of K. Okay. And one of the things I asked you to do was to find the slope of the tangent line at 5 months. Now, the issue becomes, and Matt, you can help me out here, from your data table, how much did you, from your data table, calculate Margot would lose at 5 months from your data
5
table?
months?
Yeah.
We got, 59, I want to say.
Because you have to recur, I can't just calculate that super fast.
Or it's, well, we used 0.1, so just like 59.
That's fine. What did you get for the rate loss at 5 months?
59.05.
59.05? Okay. 59.1. That's how much they figured out at 5 months. Now, how'd they get that? Because I think Matt, being Matt, decided to pick a nice, easy number that Margot would only give away 10%. Okay? Which is 0.1. So what they did is they took the amount they started at the beginning of the 5th month, multiplied it by 0.1. So you implied that roughly you had about 591.
550, or yeah, 590.
590 and 591 at the 5th month. Okay, now, so therefore, let's come back and look at some stuff, and we're going to have to continue this discussion tomorrow. If we examine each month, I'm just going to look at some of the data. 3, 4, 5. Okay. at the 5th month, if you look right here, they had 590.41. That's how much money they had that Margot had at the start of the 5th month. So therefore, by definition, what they said was the amount lost over the course of that month was $59. That's where it came from. Well, what I want to show you is, what does the tangent line say about that point? Well, if we look at the tangent line for that point, we see that the slope of the tangent line, where we thought it would be, what they thought the slope should be 59, Logger Pro says it's really negative 62.6. They're close. They're not exact. Now, the real question should be, should they be exact?
No.
And the answer is, realistically, yes.
Wait, Logger Pro is
Did us or them?
No. They should be exact. But why aren't they?
because it's an estimate.
Well, here's the problem. How is Logger Pro estimating the slope of that line? It's trying to estimate it, right? And the way it's estimating is the points around it. And as a consequence of that, since the points around it are 1 month apart, it's trying to estimate the slope of the tangent line, and it's a little bit off. But how far off is it? It's off by basically 4 and 59. Okay, roughly. All right? It's off by a little bit. But these two numbers should roughly be the same because what this is trying to tell you is what is the rate? It's how quickly Margot loses money. But what you effectively did when you generated this is you made a whole bunch of lines. Each of these represents a line, and that line goes over 1 month, and you said over that 1 month you lose this much money. The problem was, since I gave us times of months as opposed to times of seconds, we're getting kind of an average rate for each of those pieces, and that's why those two values aren't exactly matching.
So the y should equal the slope?
No. Here, the y value is how much money Margot made. What was the rule for losing money per month? The loss of money
Is 0.1
would be 0.1 times how much money she had on the first of the month. So the amount of loss per month, which is an estimate of the slope, right, is simply 0.1 in this case times 590. You estimated that they lost $59. Logger Pro is saying the slope of that point is 62. The reason why they're off by a little bit is that you're taking over the time frame of a month. I am estimating the slope of the tangent line. And just as when you draw the slope of the tangent line, you can be off by a smidge, the same thing happens here. Okay? Now, tomorrow, I'll tell you what, after our quiz, we'll pick up with this discussion. And at the end of class tomorrow, we will then decide when you want to take your test, if you want it Tuesday or Thursday. Okay?
Is that a bad idea to try to?
Huh? Yeah.
Because I had a equation I couldn't get a rate.
That's okay. That's all right. Now, remember, your quiz tomorrow will simply cover through Tuesday work, method of initial rates. It does nothing with anything with our graphs here.